All right, welcome back everyone. This is section 6.5 on solution concentration, and there are several different ways of describing concentration. In this video we're going to be looking specifically at molarity. All right, so let's start with the definition. So molarity, which is symbolized with a capital M, okay, and the capital is important because we do also have units that are described with a lowercase m. So try to make it clear that you've got a capital. Okay. Molarity Molarity is the amount of the solute in moles, so it's moles of solute divided by the volume of the solution, and the volume of the solution is given in liters. So moles of solute per liter of solution. And this is important here too. There are some units of concentration in which you've got the amount of solute divided by the amount of solvent. Okay? In this case, it's solution. So in the denominator, you want the volume of the entire solution, which includes both the solute and the solvent. So you mix them together and see what the resulting volume is after they're mixed, and that's what goes in the denominator. All right? So let's do a quick sample calculation. All right, so question is, what is the molar concentration of a solution made by dissolving 5 grams of lithium chloride in water and diluting to 100 milliliters? You might also see this written as diluted to a total volume of 100 milliliters. All right, so a couple things. The question says molar concentration. That means they're talking about molarity. But molarity is the concentration that we use almost exclusively in chemistry. Occasionally there are some other concentrations, but molarity, I would say 99 times out of 100, if someone says something about the concentration of a solution, they mean molarity. Okay? So if you see a question like this and it just says, what's the concentration of this solution, and doesn't say anything else in the question, you should assume that they're asking about molarity. Okay? All right. All right, so we want to calculate the molarity. And so by definition, this is the moles of lithium chloride divided by the volume of the solution in liters. Okay? We've got some of this information, right? The moles of lithium chloride, we don't have moles, but we know that we've got 5.00 grams. And for the volume of the solution, we know that it's 100 milliliters. We don't have that in liters yet, but we do have the volume. So all we need to do is convert this mass into moles and convert these milliliters into liters. Okay. So let's take lithium chloride first. Okay. And if you remember back from when we were doing our stoichiometry, talking about mass and moles and things like that, we can use the molar mass as a conversion factor. If you've got the periodic table, you can calculate the molar mass of lithium chloride is 42 42.39 grams per mole. Okay, so this measurement here, this molar mass, can be used as a conversion factor. We know that every every 42.39 grams of lithium chloride is 1 mole of lithium chloride. And so when we do the math there, we'll get moles, and this is 0.118 moles of lithium chloride. All right. So I'm going to put this up here because this is for our numerator. All right, so that's our numerator. Now we'll do the same thing with the denominator. We've got 100 milliliters. Apologize if this was difficult to see. That's 100. So we've got the volume already. We just have to put it into liters. And should remember that there are 1,000 milliliters in a liter. All right, so 1 liter is equal to 1,000 milliliters. Again, we cancel our units. And that gives us 0.1000 liters. We've got 4 significant figures here, so we should have 4 here. So now all we have to do, now that we've got these, the numerator and the denominator into the correct units, we just put them into this fraction. And so the concentration is 1.18 moles of lithium chloride per liter. If you want to write the answer this way, that's a perfectly fine way to write it. You could also write it as probably the more common way to write it would be to say 1.18 molar lithium chloride. That would be the concentration. All right. Lovely. All right, let's do another problem. This is a common type of problem. So we've got a stock solution. We've got some big jug in the stock room, which is a sodium chloride solution. The concentration is 1.50 molar sodium chloride. How many milliliters of that solution are needed to give 4.0 times 10 to the minus 3 moles of sodium chloride? So you're doing some kind of a reaction, or you're synthesizing something, and you need to add 4 times 10 to the minus 3 moles of sodium chloride. How much of this solution should you use? All right, typical question. All right, there are a couple of different ways to approach this. Probably come up with 4 or 5 different ways if we play around with it long enough. I'm going to show you 2 ways to do this. The first one is the way I used to do it when I first started doing these. When I was a freshman and I had Gen Chem, this is the way that was most comfortable to me. And I see a lot of people doing this on the quizzes and exams, so I think it's comfortable to a lot of students. So we'll do that, and then we'll look at another way that's a little bit more efficient. But the other thing I wanted to mention is that both of these methods are based on an important fact. And that is that concentration is an intensive property. That's true of molarity, that's true of percent composition, that's true of weight percent, that's true of molality. All different units of concentration are intensive properties. So molarity is moles per liter. And if you go back, remember when we were talking about intensive and extensive properties, one of the things that we said is that if you have a ratio of 2 extensive properties, that ratio is very often an intensive property. And moles depends on the amount of stuff. The more stuff you have, the more moles you've got. So this is an extensive property. Liter, this is volume, right? And the more stuff you have, the larger the volume is going to be, obviously. So volume is also an extensive property, but the ratio of those 2 properties is an intensive property. Okay? So the fact that this is an intensive property is important, and with regard to calculations, it's important in 2 ways. Okay. So the first one is the definition of an intensive property is one that is not dependent on the amount of stuff that you've got. Right? So concentration is an intensive property, and that means concentration is constant regardless of how much solution you've got. If you have a problem that describes a solution, like this one right here, right? This stock solution is 0.15 molar. Okay? The concentration of that solution is going to be constant regardless of whether we have a gallon of solution or 5 gallons of solution, or enough of the solution to fill a swimming pool, enough of the solution to fill a thimble or an eyedropper. Doesn't matter how much you've got, this concentration is a constant. That concentration will be true for all solutions of this, no matter how much you've got. Pour out a little couple drops, concentration is the same. Pour out a bucket full, concentration is the same. All right, that's the first thing. Second thing, The second thing, also based on the fact that this is an intensive property, many intensive properties, like molarity is one of these, are relationships between two extensive properties. Just erase this here, but molarity is a relationship between moles of solute and volume of solution. So it's a relationship between those two things. Because it's a relationship, it can be used as a conversion factor. So we can use the fact that the concentration is constant regardless of the size. That's one way that we can apply this. And the other way that we can apply it is by using that concentration as a relationship or a conversion factor. Okay. Well, let's take a look at how we can do each of those. All right, so this first one, we need to measure out some of this sodium chloride solution so that we have enough for 4.0 times 10 minus 3 moles. Right? So we've got this big jug. This is our stock solution. And it is 0.15 molar sodium chloride. Okay. We're going to tip that and we're going to pour some of it out. Maybe we'll use a beaker. Maybe use a graduated cylinder. We're going to pour some of that solution into the cylinder so that this solution solution contains 4.0 times 10 to the minus 3 moles of sodium chloride. All right. Now, the way that we can approach this is by recognizing, or one of the ways, is by recognizing that because concentration is an intensive property and is therefore constant, the concentration here, the ratio of moles to liters here is going to be the same as it is here. Okay? So, over here, our ratio, we know from the from this equation, our ratio is know that our ratio is 1.5 or 0.15 moles of sodium chloride per liter of solution. That's the concentration here. Okay. The concentration over here is also 0.15 moles sodium chloride per liter of solution. Okay. But we're not going to write it that way. We're going to use the volume and the number of moles in this solution. So for this solution here, we know that our number of moles is 4.0 times 10 to the minus 3 moles of sodium chloride. Our volume, we don't know. Our volume is going to be our variable, right? So we can just put an X there, right? But we know that whatever this ratio is, it's going to be the same as this ratio because concentration is an intensive property. All right. Okay, so now all we have to do is a little bit of algebra. And if you remember from algebra or middle school, maybe high school, if you've got two fractions that are equal, you can solve for x by cross multiplying. Okay? So this means that 0.150 moles of sodium chloride times x is equal to 1 liter of solution I'm going to erase this here, but 1 liter times these two, right? So we're taking this and this, multiplying by this and this. And then in order to solve for x, we just divide both sides by this part here, right? All right, so we can look at this and already feel like we're probably doing a good job, because if we look at our units, moles of sodium chloride and moles of sodium chloride are going to cancel out, and our units are liters. That's good. We wanted a volume, so the fact that we're ending up with liters tells us that we're probably doing a good job. So for our calculation, just take 1 times 4 times 10 to the minus 3 divided by 0.15. See what we get here. All right, I got 0.02666. It's actually repeating 666666667. Okay, and our units are liters. Okay, all right. A couple of things. We'll look at significant figures. We've got 3 significant figures here, 3 significant figures here, so we should round this to 3 significant figures. Okay. And also, the question asked us to give that result in milliliters. So let's go ahead and convert that from liters to milliliters, remembering that 1 liter is 1,000 milliliters. So we got 26.666667 milliliters. Again, you want to round that to 3 significant figures. So the volume that we would need is 26.7 milliliters. And we could measure that out with a graduated cylinder. All right? Okay, so this is a fine way to do this. Right? We're using the fact that the concentration is an intensive property and doesn't change. We set up 2 fractions. And you could do the same thing if you had the volume and you were trying to solve for the number of moles. You could do it exactly the same way. You would just make x here. You just make your variable be the moles instead of the volume. Okay? So you set up 2 fractions, set the 2 fractions equal to one another, cross multiply, and do a little bit of algebra. Like I said, that was the way that I used to do these, because that made sense to me early on, and I see a lot of people doing that on their calculations on quizzes and exams. So if that works for you, that's great. Okay, but I want to show you another way, and this is a little bit it's a little bit more efficient. And one of the nice things about this is you can incorporate this with other calculations, so that you can string a bunch of calculations together and do more complicated problems using the same method. Okay, so this is, I guess I would say this is a better way to do it if you can get to the point where this works well for you. Okay, so what we're going to do is we're going to use dimensional analysis. Okay, so for dimensional analysis, we take what we want to get, what we know about our solution. We know that we need 4.0 times 10 to the minus 3 moles of sodium chloride and we're trying to determine what volume would be required. Okay. So we can use this. Now we're going to take this molarity okay, 0.15 molar sodium chloride, and we're going to remember that because this is an intensive property, it's not just a number, it's a relationship. And the relationship that's described by this concentration is that 1 liter of solution is equal to 0.150 moles of sodium chloride. And if these two things are equal, then we can use this to make a conversion factor. So 1 liter of solution divided by 0.150 moles of sodium chloride is a fraction equal to 1, or or 0.15 moles of sodium chloride divided by 1 liter of solution is also a fraction equal to 1. So we just have to figure out which one of these we need. Since we're trying to go from moles to volume, we want our moles to cancel out. So we'll use this one, put our moles on the bottom. That way moles will cancel with moles, and we'll get our volume in liters. Okay? So let's put this in here. So we're going to use that molarity as a conversion factor. And when we do that, moles of sodium chloride cancel. We get liters. And just as we did before, we get 0.026666667 liters of solution. We want to convert this into milliliters. So if we take the volume in liters, multiply by 1,000 milliliters per liter, we get 26.66667 milliliters. Again, 3 significant figures. So we get 26.7 milliliters. All right. Okay. Now, quickly, I want to show you why this method is a little bit more convenient. Okay. We use this to go from mole to liters, and then we did another calculation here to go from liters to milliliters. Okay. But if we've been thinking about that from the beginning, we could have said that we want to convert from moles of sodium chloride into milliliters, right? And then we could use this conversion factor to convert from moles of sodium chloride to liters of solution. Right. And then we could use this conversion factor to go from liters to milliliters. Okay. so we can do the whole thing in one step instead of, well, I don't know whether you want to call it, I'll call it one step. We can do this in one calculation rather than two calculations. So now our moles of sodium chloride cancel, our liters cancel, and you can put that in your calculator. And you get 26.66667. Or 26.7 milliliters of solution. Okay. Right. So use whichever one's more comfortable to you at first, right? So that you can feel confident about what you're doing. But I would encourage you to try to move toward this type of a calculation, this dimensional analysis approach, eventually, because that's going to be more efficient for your calculations throughout the semester. All right? All right, I think that's a decent place to stop on this one. Yeah, this is a good place to stop for this. There are lots of study problems and practice problems. Work through those and let me know if you have any trouble, and we'll see you again next time.